Yes. So thank you for letting me present here. So this is a presentation about a paper also about bin packing, and this time we're looking for a fast exponential time algorithm for the exact version of bin packing, where we see the number of bins as a constant. And this is joint work with Jesper Nederlof, who's my PhD supervisor, Jakob Pavlovic, and Karol Wojcinski. So just to be sure we're all on the same page on bin packing, we're given n items, and each item has a given weight, Wj, and the weights are positive, or they're a natural number. And I also will denote W of x, where x is a subset of the items, as just the sum of the weights of these items. So it's actually what you would expect. And then we have m bins, and the bins have a capacity C, and we then want to know, can we just distribute these items over these bins? So in this example, we have a couple of items with different weights, and we have 4 bins here with capacity 8, and the question is, can we distribute them? And this is the S instance because we can. Okay, so how can we solve bin packing if we want to solve it exactly? There's an algorithm A, which I would describe as a dynamic programming algorithm, and this runs in time C, so that's the capacity, to the number of bins times n. I'll get later into this algorithm a little bit more. And there's also another algorithm that you could use as algorithm B, I'll call today, and that's an algorithm based on methods from Bjorken, Buswell, and Kirivisto from 2009, and this runs in 2 to the power n times n, and so that's a pretty nice algorithm, but as I am a PhD student of Jesper, I asked the question, can we do something faster? Can we do something better? And we didn't answer that specific question, but we did if we see the number of bins as a constant. And so that's what we're going to do today. So our result is we can do something that's 2 minus epsilon m, where epsilon is some constant depending on the number of bins, and it's small. But it's definitely bigger than 0. This was already known for m is 2 because that's subset sum, and there's mean in the middle in 2 to the n over 2. And it's actually also already known for m is 3, and that's a result by Lente, Liebloff, Sokal, and kind of 2013 by a sort and search algorithm. But for all the other m's, this was unknown, and so we actually included these. The idea of the algorithm is as follows. Either algorithm A is going to be faster than 2 to the n, or some variant of algorithm B is going to be faster than 2 to the n. And which one is going to be faster depends on 2 parameters, which I'm going to be talking about a lot in this presentation, so please do remember them. So alpha of W is the number of different weights that the weight function generates, as I would call it. So it's all the different weights that I have if I take subsets of the items. And B of W is the maximum number of sets that have the same weight S. So S will be defined later. So it's just the number of different sets that all have the same weight. And now I will prove this presentation later that either this alpha of W is going to be small enough, or this B of W is going to be small enough. And so the presentation will be as follows. First, I'll explain how we can use this fact in algorithm A. Then I'll give you an idea how we can use the fact of B, W being small to get something faster in algorithm B. And then I'll quickly try to give you an idea of why we can indeed assume that one of these 2 is small enough. So first, just to really be sure everyone's on the same page, I just want to have a quick example. So for example, alpha of W, if we have only 5 items and they're all having weight 0, then alpha of W is 1 because we only have weight 0. That's the only weight that's being generated. And there are 32 different sets that all have this weight 0. And on the other side of the spectrum would be if we have, for example, powers of 2, so 1, 2, 4, 8, and 16. Then we can generate the weights 0 up until 31, so 32 different weights, and each one of them has a unique weight, so B of W is 1. Okay, so algorithm A. I told you already it's a dynamic programming, so we have a table entry and it's indexed by the items 1 till j. So J stands for I want to schedule, sorry, not scheduling today, we're thinking. I want to do items 1 up until j into bins with the leftover capacity C1 up until Cn. And it's yes if that's possible, and it's no if it's not. And we can compute it like this. So what we're going to do is we're just going to check for item j, we're just going to put it in some bin. In this case, it will be bin I. We subtract the weight from that bin, and we want to say, can the rest of the items now fit in the new leftover capacities? So this will give us a runtime of c to the power m times n squared, because the number of different table entries that we have, we need to compute for every Ci, and that's between 1 and the capacity, and there are m of them, so that's c to the m. But we can do something better once we know that the number of different weights that we are generating is small, because we don't need to actually compute the Ci's for all the Ci's. For example, if I only have even weights, it would be weird to compute something for an odd number of capacities, because it's not interesting anyway. So we only are going to compute the Ci's for the ones that actually occur in our weight function. And with this, we get a new runtime that is alpha of w to the power m times n squared. And so we can conclude that if alpha of w is small enough, that means smaller than 1.99 to the n over m, if we just fill it in the formula, you can indeed see that we can get something that is faster than 2 to the n. So that's the first part of the algorithm. Let's go to the second algorithm, algorithm B, which is a bit more complicated. So for this algorithm, we're going to use the following theorem. And it says that if we have B, a set of sets, B, set of sets, so x1 is a subset of the items, x2 is a subset of the items, etc., then we can compute in time relative to the down closure of B, and that's all the subsets of a set of B. We can compute in that time whether for each x, if it can be distributed over n bins. So for each of these sets, I'm going to have either yes, I can distribute it over n bins, or no, I cannot distribute it over n bins. And we can do this because of fast algebraic transformations, which is set of Laplace transformation in this case. Okay, so how are we going to use this? Well, I'm going to make an assumption today, and the assumption is that half of the items fit exactly in half of the bins. So that's quite an assumption. Believe me, we have kind of like 4 cases where each time we have a different algorithm, and this is one of the easier cases, so this is the one that we're going to stick with today. So we're going to assume that half of the items will be in first half of the bins, and the other half will be in the other half of the bins, but we don't know which half of the items will be where. So to find out, we have this set B, and it's going to be all the sets that are of size n over 2, so that's all the sets that could possibly be in one of the halves. And then we also have that the weight should be exactly such that it fits in one of these half number of the bins. So it's m over 2 times the capacity. So it's indeed exactly what would fit into m over 2 bins. And then we use this algorithm, this theorem, and we compute for each of the x's in B whether it fits in m over 2 bins, but we also compute for its complement whether it fits into m over 2 bins. And now if we have for some set that both x can be distributed over n bins and its complement can be distributed, then we know that the whole set can be distributed over n bins. So we have yes. And the time analysis, the runtime analysis, so we have to look at the down closure of B. And this is where we use this fact that B of W is small. So see that B, we actually restricted all of these things to be of a certain weight. We say that the weight of X should be equal to C times M over 2, so it's a very specific weight. And so if we combine the number B of W, then we can also bound the size of B. And since B lies roughly around all these items of size n over 2, we can then conclude that also the down closure is something smaller than 2 to the n. It's a bit hand-wavy, but I hope you get the gist of it. So in this case, we also conclude that if V of W is smaller, then again we get a fast enough algorithm. Just to conclude, we have these two algorithms, and both of them run fast enough if we have these alpha of W being smaller enough and V of W being small enough. And now we still have to prove that indeed one of these cases is true. And we do this by a theorem, which is that for all delta greater than 0, there is an epsilon greater than 0, such that if this alpha of W is greater than 2 to the delta n, then B of W is at least smaller than 2 to the n. And this indeed gives us what we want, because if we take delta equal to 1 over m, so here you see where the dependence on the machines comes in. Because we take delta 1 over m, so then either alpha of W is small enough for algorithm A to work, and if it's not, then we can use the theorem that tells us that indeed the other side is fast enough. So how to prove this? So this is where we use additive combinatorics. So if you didn't follow anything from the last few slides, you can just come back again, because it's a kind of a different topic. We're going to use additive combinatorics for this. And more specifically, we're going to use unique decodable pairs. So uniquely decodable pair is two sets A and B. And we want to have that if we element-wise sum these elements, then the sizes of A times the size of B should equal to the sum of these, the sum elements of this. Where I want to note that the sum is actually addition over the integers and not modulo 2 or anything. So let's just look why we're, like, what is this? Why we're looking at this. So you can imagine it like following. There's 3 persons and a red and a blue person, and they try to communicate something to the yellow person. And the red person has access to this library of words A, and the blue person has a book B where you can choose words from. And now they send their message, but their message is being summed, and that's what the orange person receives. And we now say that A and B are uniquely decodable if this orange person can always find out what the person's actually sent. Just a quick example, just to make it up. So there's A. For example, we could say first person A can only communicate over the first bit, and B can communicate over the second and third bit. Well then, I hope you'll agree that we can still find out what the people sent. And a more complicated example would be if we have A having 1, 0 and 0, 1, and B having 0, 0, 0, 1, and 1, 1. And in that case, we get 6 different sums. And also we have 2 times 3 different messages that we have. So indeed, we see we have this uniquely decodable pair. So why am I going on about this uniquely decodable pairs? Well, I've been showing you uniquely decodable pairs from the beginning of this presentation. So let's look why that is indeed the case. And before I show you this, I just quickly want to rephrase my weight function. Before I just said it like W of X. But I just want to see it as an inner product. So X is now 1 if it has an element in, and a 0 if it doesn't have an element in, and I just take the inner product of X and W, the weight array. And then I take A to be all the sets that have different weights. So I look at all the different weights that I generate. And then for each weight, I pick exactly one such set and I put it in A. So that's my A. And then my set of A is going to be equal to alpha of W. And for the set B, I'm going to have all the B's that have exactly this weight S. And again, I hope you agree that B is then equal to B of W. And I'll show you now that A and B are UBCP. So let's see B the received message. So the orange person receives C, and he knows it's a combination of A and B. And we also know that the weight function is just linear, so we know that it's a combination of some weight of A plus some weight of B. But we know what is the weight of B, because everything in B has weight S, so we also know what is the weight of the thing in A. And everything in A had its own different weight, so know exactly what message A was sent. So now we know A, And then we can do some very high mathematical, we can also find out what is B by just subtracting B, C minus A. Okay, so I hope you agree that A and B is UDCP, and we want to use the following bounds on UDCP. So there are already some bounds on UDCP. So for example, there's Tilburg 1978 that says that the size of A times B is almost 2 to the power 1.5n. And this would help us, for example, you can now say that the size of A is equal to the size of A times the size of B, and then divide by B. Oh, sorry, there should be a plus there. That's a mistake. But then you can see that we can bound the size of A by the size of B in some sense if B is large enough. There's also another bound by Hausdorff in 2018, which is of a little bit different flavor, but more of the flavor that actually we're going to need. So it says that alpha is at least something smaller than 2 to the n, then B is bigger than 2 to the n, and yeah, B is this function here. But what we need is a little bit different, because we want this delta to really be quite small. We want it to, like if we have 100 machines, then we need delta to be really small. So we have to prove our own little statement about this. And this is how we were able to do it. So instead of just looking at A and B as I previously defined, we're going to look at a set that I call K times B. And K times B is a set where I just sum K things from B. So that's all these different sums. And then I noticed that because I sum K things from B, I now again have everything in K times B having weight K times S. Because I sum K things that have weight S. And now I use the same argument as I did on the same, like 2 slides ago, that these new A and new K times B, they're also UDCP. So they're not really UDCP because K times B doesn't live in 0, 1 to the n, but the property that A plus K times B is equal to the size of A times the size of K times B, that still holds. And now I actually have time for this, I'm surprised. I just want to give you a flavor of how this helps us and why this is so powerful. So let's now assume that B is almost everything. So B is almost of size 2 to the n. Then this set B is roughly everything in 0.1 to the n. And then this K times B will be almost everything in 0 up until K to the n. And everything in A plus K times B will now, so A still lives in 0, 1, so I just sometimes a 1 to things in K times B, so it now lives in 0 to the K plus 1 times n, to the power n. And then I can roughly bound by this K plus 2 over n divided by K plus 1 over n, very roughly. And then I get this 2 to the power delta K n. So I can make my delta smaller as my K goes to infinity. So I can make it as small as I want. So this is how the construction of our proof actually goes. Yes, so I think that's everything I wanted to tell you. So, yeah.
Sorry, so in the bound, where did you use, like what assumptions did you use in the inequalities? Like, I mean, the UDCP assumption is used where?
The UDCP assumption is used in the very first one. So I bound the size of A by the size of A plus K times B divided by the size of K times B.
Where is that equality?
It should be equality.
Okay.
Yeah.
I see.
Yes. Yes.
And then where did the K plus 2 come from?
So everything in here lives within 0 up until K plus 1. So it has K plus 2 different numbers that you can choose from to the power n.
Okay. Right. All right. But so nothing in the remaining sequence of inequalities is using something deep. I was just making sure.
Yeah, so if you actually want to prove it, there's a lot of technicalities in the fact that we assume that B is close to being everything.
Okay.
So that was actually quite some work, and there's also...
Oh, that's why there's a little...
Yeah, there's
less in your... Okay, I see.
This is just how we came to the idea of this should work.
I see.
And then we still have to
very
prove
good.
it, but
Okay.
I'm not going to bother you with, with the technicalities. Okay. So to conclude, we are able to do bin packing faster than 2 to the n if we see the number of bins as a constant. So that's pretty cool. The key idea is this trade-off between alpha of W and B of W. And for future research, it would be awesome if we could also get bin packing faster than 2 to the n, but m not a constant. But you definitely need some extra or new insights, because everything in here is very dependent on this number of machines, number of bins, I think. So thank you for listening.